Hello, welcome to my RTOS logics videos. This video is in continuation to my previous video which demonstrated synchronization between an ISR and a thread. Here in this video I have tried to simplify and explain synchronization between interrupt service routine and thread and communication between multiple threads. Let's consider this example of a quadcopter where an input device can be a wireless remote controller sending RF signals to the receiver which is sitting on the quadcopter, which in turn controls the four rotors on the four sides, therefore controlling the flight of the quadcopter. So with the help of this example, we will understand synchronization between interrupt service routines and threads using binary semaphore and inter-thread communication using message queues. Okay, and I have explained in my previous videos about types of semaphores supported in any real-time operating system. Let's make use of a non-mutex binary semaphore for the purpose of synchronization. So let's say we are going to use a real-time operating system on this embedded system quadcopter and try to understand synchronization between ISRs and threads. So in this example, let's create a main thread. The first thing main thread does is registers an interrupt like we did in the previous example. So this is the interrupt service routine and this is the hardware interrupt number for which we are trying to register this interrupt service routine. Okay, then create a non-mutex binary semaphore with its initial state as not available for the purpose of synchronization. And note here, we will be creating a message queue in order to exchange messages or data between two threads. For the purpose of inter-thread communication, we will create a message queue. Any RTOS provides the mechanism of a message queue for inter-thread communication purposes, and it has its own set of APIs to create a message queue, send a message to the message queue, receive a message from the message queue. Okay, and then create two threads, one which reads and decodes data from the input device, that is a remote controller in this example, and another thread which controls the four rotors. Okay, so we have created two threads, one which reads and decodes data from input device and other which controls the four rotors on the quadcopter. So data reading thread needs to be of lower priority than rotor control thread. So this is how we have assigned the priorities to each of these threads. Data reading thread needs to be lower priority than rotor control thread. So rotor control thread is a high priority thread. Okay, so we will start with the rotor control thread which is of high priority. This high priority thread or task starts executing. Put it in infinite while loop. So before performing instructions to control the four rotors of the quadcopter, let us receive the message from the message queue which we created in the main thread. This message or the data would be required to control the rotors for the required flight or altitude of the quadcopter. Okay, so but since there is no message in the message box yet, I mean the message queue is still empty, there is no message in the message queue, this task gets into block state or waiting state. Okay, so since high priority thread is in block state, low priority thread gets chance to run, which is data reading thread. So this thread is also in an infinite loop, and first thing this thread, data reading thread, does is acquire the non-mutex binary semaphore which we created in the main thread with the initial state as not available. and since the semaphore was created with its initial state as not available, this thread gets into block state as well. So at this point both the threads are blocked. Rotor control thread is blocked for message queue and data reading thread is blocked for binary semaphore. In other words, these threads will not process further or will be waiting until interrupt is triggered. Now let's see what happens when an interrupt is triggered. So when hardware interrupt is triggered from the wireless remote controller, in this example ISR gets called. So this is the body of an interrupt service routine, body of an ISR. An ideal ISR body should look like this. First thing it does and first thing it should do is lock all other interrupts, so that when this current interrupt is getting serviced, other hardware interrupts should not be triggered, should not be occurred. So to lock all other interrupts, any real-time operating system provides an API. So using that API we will lock the hardware interrupts. And one very important thing to be noted is an ISR function body should be as short as possible, like we have seen in my previous video also, and I have explained in my another dedicated video on ISR as part of my RTOS logics videos. Please do not forget to watch it. Okay, so after locking interrupts, read the hardware interrupt registers and then signal the thread which was waiting for the interrupt to occur by releasing that non-mutex binary semaphore. Once these two important things are done, then here call the RTOS API to unlock the interrupts which we had locked earlier. And once ISR is completed executing, and since it has released the semaphore, since the ISR has released the semaphore, which means the semaphore is available now, out of two threads which were blocked, the data reading thread, which is of low priority thread, gets unblocked, as it is now successfully able to acquire the semaphore. Please keep a watch on the semaphore state as well as I talk. Semaphore acquired by data reading task. So state of semaphore is not available again, and this thread can continue further executing as high priority thread is still blocked, still waiting for message queue. So what it does next is performs data reading task or data gathering task, and once these instructions are completed, or once it completes with reading or gathering all the data it needs, it passes the data in the form of a message using a message queue. So it passes the data to the message queue. So this thread sends message to message queue using an RTOS API. Okay, let's say here we use the RTOS API to send the message to the message queue. Now note, as soon as data reading thread fills the message queue with the message, with whatever data it has gathered, the thread, that is rotor control thread, gets unblocked or gets into ready to run state. And since rotor control thread is of high priority than this thread stops execution instantly at this point and switches to rotor control thread. So note that at this point preemption has happened, or a context switch has happened. It is called preemption because low priority thread is preempted by high priority thread. In other words, high priority thread has preempted low priority thread. So rotor control thread resumes execution from where it was blocked. Right, both the threads are ready to run, both the threads are okay to run, but low priority thread stops executing instantly because it's of low priority, and high priority thread gets the chance because that also is in ready to run state now. So rotor control thread resumes executing from where it was blocked. So now this thread is successfully able to receive message it was waiting for and continues further execution. So here it calls an RTOS API to receive the message from the message queue. It collects in this buffer. Okay, so with the help of this message or data it has received, here are the instructions it will execute, which is nothing but actually to control the 4 rotors of the quadcopter. So this is how synchronization and message passing between thread works. In summary, rotor control thread is waiting for data reading thread to send data, and data reading thread is waiting for interrupt to occur. And when an interrupt occurs, interrupt service routine signals the data reading thread with the help of a non-mutex binary semaphore. So this process continues for n number of times. Let's quickly see next cycle. Once the instructions to control the rotors are completed, it loops back. Since it is in while loop, this thread again tries to receive message from the message queue, and since the message queue is empty, it is again blocked at this point. And now, since the high priority thread is blocked, low priority thread, that is data reading thread, gets the chance to run, which was earlier preempted at this point. So this thread also loops back and tries to acquire the binary semaphore, and since semaphore is not available, this thread also enters into block state. So that's all. This thread is waiting for interrupt to occur, and this cycle continues n number of times. Thank you. As part of my RTOS logics videos, please watch my other videos listed on the screen. Please watch and please subscribe to my channel. Thank you. Thanks for watching.